Hello and welcome to Pseudocode. In today's video, we are going to discuss a slightly different topic which has been on my mind for some time now, dynamic programming. I am not going to explain each and every detail of how to solve dynamic programming problems. Rather, I would try to explain the mindset that is required in order to solve DP problems. So, let's get started. When I started with one of my courses in my master's, that was the time when I really understood what is the core in order to solve DB problems. And today I would like to share the same with you. When we try to solve any generic programming problems, we have this mindset where we try to apply a brute force solution and then optimize that solution, and then we try to dry run. Instead, in DP problems, that same mindset does not work, and that's why we find it hard in order to solve DP problems. Let's take an example. Let's say that the problem at hand is to find the sum of all elements in a given array. It's a very simple problem. You can just apply a brute force solution to traverse through the array, find the sum of all the numbers, and just return the solution. While solving this problem, I can explain how our mind works. When we are trying to traverse the array, this is how we see the problem. We see the first element, we will add the second element in the first element. We will try and maintain a variable sum which we will start at 0 or initialize at the first element of array, and then we'll keep on adding the rest of the elements of the array in order to find the total sum. So we will just solve it from the starting of the array, and we will say, okay, 4 plus 5 9 plus 6 15 plus 7 22 plus 11 33, and then 35 and 38, and then finally 59, and then we return this sum. This sounds very simple to us because we have practiced a lot many problems of similar type, and we understand that we can just start from the start of the input and make our way till the end of the array or any given table, and that's how we have solved many problems. And the exercise that I have done right now, we call this a dry run. From a very simple problem like this to a complicated problem where we solve trees and linked list, we can apply the same approach where we take an input, we try to traverse through that input, try to manipulate that input, and then finally give out a solution. Sadly, this approach doesn't work for dynamic programming problems. And here is why. In dynamic programming problems, we have this concept of sub-problems where one problem keeps occurring again and again, and our job is to find the solution to that sub-problem and then utilize the solution to that sub-problem in order to reach the final solution. This is the crux of dynamic programming problems, and hence we have to move from that mindset of traversing through the input and figuring out a solution. Instead, we have to stop thinking about the input and we have to start noticing a pattern that where the problem that we are being asked to solve, what are the sub problems, how can we break that problem into smaller sub problems, and how can we utilize those sub problems to reach the final solution. This is what we have to do in DP. Now, the problem is, how do we do that? It sounds very simple when we try to explain it in words, but how do we actually do that? There are just two simple steps in order to attack any DP problem. Those two simple steps are: first, find a sub-problem and try to define it in words. And second, try to convert that sub-problem that you have defined in first step into mathematical recurrence relationship. This is the crux of any DP problem or majority of the DP problems. Now, let's try to understand that using an example. You can see there's the problem statement on the screen. This problem describes that you have a vehicle and there are certain checkpoints on the road that are given to you. You have to reach from point A to point B by passing those checkpoints. Those checkpoints are available to you so that you can refuel your vehicle. At any given point of time, your vehicle can go up to 200 miles in one full refuel. So let's say you started at point A and point B is 200 miles. If you have fueled at point A, you can reach B without stopping in any of the middle checkpoints. That is the constraint given to us. But at every checkpoint that you stop at has a penalty associated with it. So basically, you have to pay a fee or you have to pay a penalty at any point when you stop at any checkpoint. The objective at the end is to reach from initial destination to final destination with minimum penalty. You have to optimize the number of checkpoints that you stop at with their associated penalty in such a way that the penalty you pay is minimum possible in order to reach your final destination. Let's take a concrete example and see. You are given three checkpoints: 100, 150, and 300. Let's name them as C1, C2, and C3. C0 is your initial starting point. And with every checkpoint, there is a penalty associated: P1, P2, and P3. Now, you have to drive from C0 to C3 such that the penalty that you pay is minimum. If you will apply a generic programming problem solving approach here, this is how you would try to solve it. You will think, I am at C0. Can I get at C1 from the fuel at C0? Yes, you can get there. So you don't have to stop at C1. And then you will try to see, can I get from C0 to C2? Again, since you have full fuel at C0, you can reach C2. So you say you will try to skip C2 as well because you can go up to 200 miles. Now, can you reach C3 from C0? No, because you can go maximum up to 200 miles. So you will think, okay, no, I would have to stop at C2. But now you cannot do that anymore because you already surpassed that point. When you were at C2, you thought, okay, I can drive till C2 or more than C2 because C2 is a distance of 150. And hence, this traditional approach doesn't work here. Now, here comes the mindset shift. What you actually have to do here. One more part of the problem that I forgot to mention was, at your final checkpoint, you have to refuel. So if 300 is your final checkpoint or whatever is your final checkpoint, you have to pay the penalty at that point because that is your final destination. So in any case, your penalty too would have to be paid in whatever solution we design. Now, coming back to the mindset. In this particular case, we can start from back rather than from front. So, if I am at 300, if I am at checkpoint C3, what are the possibilities in order to get to C3? I can get to C3 from C2, from C0 to C2 and C3, or I can get to C3 from C1 and C0, or I can get to C3 from passing all the checkpoints from C0, C1, C2, C3. Again, this doesn't sound very optimal. Let's try to refine our approach. Let's say that when you are at C3, you only have to figure out from which point you have come to C3. Either you have come from C2, or you have come from C1, or you have come from C0. We do not care where did we reach the previous point from. So at C3, you will only check, have you come from C2 or C1 or C0. Okay. Now, given the inputs, you could have reached C3 from C2 or you could have reached C3 from C1. Let's say that you have reached C3 from C1. In that case, the penalty that you would have paid would be, at C1 you would have paid 10 and in C3 you paid 2 and the answer is 12. If you reached C3 from C2, then you would have paid penalty 18 at C2 and then 2 at C3, so 20. These are the two penalties that you could have paid at C3. Now, let's say that you have taken this path. If you have reached C3 via C1, you could have reached C1 from C0, so there is no penalty there. If you have taken this path, C3 from C2, then there is a possibility that you have reached C2 either from C1 or from C0. If you have reached C2 from C1, that means you have paid penalty 10 at C1. If you have reached C2 from C0, then you haven't paid any penalty. If you have reached C2 via C1, then the total penalty to reach C3 would become 10 plus 18 plus 2, which becomes 30. However, if you reached C2 from C0, then your penalty stays 20. If you have reached C3 from C1 uh, and you didn't stop at C2, then the total penalty is 12. Now, the most optimal solution out of this one is 12. So you have to traverse through all these possible solutions and then try to pick a minimum. If we will try to define our subproblem in words, it would be this. Because at any point of time, we are trying to figure out total penalty at that particular point. So let's say that I'm trying to find out total minimum penalty in reaching a point I from any point J like the previous point j, where j can be from j I minus 1 to 0. And also I have to take care of the constraint that the point that I have come from, let's call that point cj. So the constraint that we have to take in mind is the distance between that point cj, or I would have to write it as ci. The distance between current point ci minus the point that we have come from cj should be less than equal to 200, because let's say in this case we could have reached c3 from c2 because the distance between both of them is 150, and we could have reached c3 from c1 as well because the distance between both these points is 200. But let's say that c1 would have been 50 instead of 100, then there is no way we could have reached c3 from c1, so we have to discard this point. We only have to take one of those previous points such that the distance between that point and the current point that we are considering is less than 200. And hence, when we are defining our subproblem, we need to handle this constraint as well. So this is our subproblem. Now, the next step is to write this problem in a mathematical formula or in a recurrence relationship. So this is how we are going to write it. That the total penalty at a point ti, in this case c3, is PI, the penalty at that point, because in any case you're giving the penalty at the point where you have reached, plus we have to take one of the minimum penalties of reaching to this point from a previous point. So let's say that the previous point that we reached here was j. How will we find that j? We will traverse j from I minus 1 to 0 such that ci minus cj is less than equal to 200, and then we will find out the minimum penalties from that one, and then we add that minimum penalty to our current penalty, which will give us the total penalty at reaching at point I. And when you do this for your last point, you get to your final solution. The important part here is not the solution. The important part here is that we started from the end of the array rather than starting from the starting point of the array. In some problems, we would have to start from middle of an array or middle of the input. The input to a dynamic programming problem could be a table, could be 2D arrays, could be single arrays, or anything else. All you have to figure out is to try to find a point in the middle or in the end so that you can reach your subproblem. It doesn't matter which point you pick. You just have to ensure that you are trying to find a subproblem in a way that the solution to that subproblem can help you to reach the final solution. So, and this is the crux of dynamic programming. I have attached the pseudocode for this problem, the solution to this problem, in description. You can convert it into real code. You can write some test cases and try to run this code and see for yourself how does it perform. If we talk about the complexity of this code, it will be n square because we are using two loops. However, the objective of this video was not to tell you or help you practice dynamic programming problems. It was just to give you an introduction to what is the crux of dynamic programming problems. Now, if I want to summarize it, do not try to dry run any solution from the starting of the input, or do not try to have the same mindset that you have in generic programming problems. There is a mindset shift, which is you have to try to find the subproblem and generalize the solution of that subproblem to reach the final solution. And then again, once you find that subproblem, you have to write it mathematically in a recurrence relationship. Once you do that, your problem is solved. Then writing the code to solve that is actually the easier part. The difficult part is to find that subproblem and find a representation for it mathematically. Once you practice these two steps with some of the dynamic programming problems, you will be able to get a grasp of it in no time. If you like this video, you can let me know in comments, and then we can work on similar videos around this topic if you need help with the same. Till then, take care. See you in the next video.